Good afternoon. So, is there any questions from the previous class? Was there any question? So, in the last class, we briefly looked at different aspects of electronic devices and circuits. Okay. So, I mentioned like we have two different tracks. So, you can study the devices, its fundamentals. Okay. That means essentially IVCV. And for that, we need to know very basic things, right? Basic quantum mechanics crystal structure. So we'll build up on that and we'll then continue on this, okay? And there was another aspect which is on circuits. So we have wide variety of courses as we discussed in last class. So you can accordingly choose, okay? Yeah, so these are overall broad areas, okay? So here also we discuss the content. So essentially we have three modules. The first module we have basics or fundamentals. Okay. Essentially we'll talk about crystal structure, uh, very briefly quantum mechanics, whatever needed for this course. Okay. Then we'll see energy bands and so on. And after that we'll uh, continue our discussion to semiconductor junctions, for example, PN junctions, okay, metal semiconductor oxides, and then we'll move towards transistors, okay, MOSFETs, and also we'll cover some of the optoelectronic devices, okay. So here some of the textbooks we have suggested. Also, I mentioned the grading schemes. There will be typically 4 quizzes and N minus 1. So typically 3, okay, best of 3 will be taken. So we will have 4 quizzes and 2 exams. So altogether we'll have 6 exams, okay? And roughly we have 24 to 26 lectures. That means we'll have either quiz or exams per 6 lecture. Okay, so 1.5 weeks. So that means the first quiz will be on mostly on this crystal structure, quantum mechanics, and maybe something related to band structure. Okay. Okay. So this was the statistics last time. Yeah. So then we looked at what are the materials, because here we are interested in on semiconductors, right? So we identified elemental semiconductors like silicon, germanium, and very briefly I mentioned that there are band gaps, conductivity. Those are the things we'll gradually study. Okay, so we talked about elemental semiconductors from group 4, and I said that you can combine group 3 and group 5 or group 2 and group 4 compound semiconductors. Then also we can have alloys, right? So I have shown some devices, right? I hope you remember, and also the wafer, okay, on which semiconductor devices are fabricated. So if you look these materials or devices under microscope, you will find this kind of crystal structures or crystallinity. Okay, so some of the materials will be single crystal. For example, the materials of our infrared silicon germanium, these will be single crystal, where we have ordered, okay, crystal ordering is important. So polycrystal, amorphous, these are the things we discussed, okay. So now since silicon, germanium, these are single crystal materials, so we need to know crystal structure, okay, and we'll see that later on, depending on the orientation, properties will also change, okay. Yeah. So this is the beginning. So we started with this definition of lattice, periodic arrangement of points, right? These are the things we discussed. And we can have shells, okay? And we can repeat them and reconstruct the entire surface without leaving void. Some of the cells will have the minimum area or volume. We call them primitive cells. And therefore, we have primitive vectors, okay? Yeah, these are the things we discussed. Again, just to recap you, this choice of primitive cell and primitive vectors are not unique, okay? It's not unique. These are the things we looked at. Yeah, then we asked the question like what type of lattice it is, and eventually saw that this is not a Bravais lattice. For example, this 1D chain is periodic, but this is not a Bravais lattice. You have to combine them. This is very important property, okay? Because in crystal, it is not that only we'll have points, we can have different molecules to that point. So, okay, those are called bases, okay, or atoms per site, okay. So we need to combine them or group them together, and then we will get into Braville lattice. So this is a classical example 1D chain. Okay, so we can do the same stuff with 2D, and of course there are 3D examples. Okay, so now, so these are the things we discussed. Okay, then I mentioned that there were 5 different types of Braville lattice. Okay, exist in 2D and 14 different types of 3D. So we talked about rotational symmetry. So some of them are 4-4 symmetric, 2-4 symmetric, okay, 6-4 symmetric, and this is 1-fold, meaning 360-degree rotation you need. And also I mentioned one thing that put some centered atoms, okay, and see if you get any type of new crystal, okay. So I think there was some confusion, so we just very briefly recap on that, okay, soon. Okay, so now we can extend this idea to 3D, okay? So this simple square will become cube, so on and so forth, okay? And keep putting the center atoms, okay, accordingly. So there are 14 different types. So let's very briefly revise. So we had a little bit doubt probably in the last class. So I hope you understood this one, right? So if we take rectangle, then if I have the center atoms, then it is a new type of crystal. Okay, so the new type of crystal, the reason is, so here the primitive cell is a rectangle, okay, but here the primitive cell is rhombus or parallelogram, okay, and it has 180-degree crystal symmetry, okay. It doesn't need to be a rectangle, okay. Okay, that's point number 1. So point number 2 is, there was also a question that how about if we have square lattice, okay. I think there was some discussion, okay. So now if I put center atoms here, what do you get? What kind of lattice do you get from this? Okay, now this is our new, it is square. Square becomes square, okay, it doesn't change, okay, that's important. So you can have rhombus or different shapes, but the minimum one, a primitive cell is square, okay, it will not be changed. Yeah, so you can, I mean, you feel free to take any combination and accordingly put this kind of center atoms, and you will find different combinations, but eventually those will fall one of these 5 classes. Maybe you can extend, yeah. Here, here. This is square, right? So here, this is square.
Can we take 2 bubbles and
Here. Then if you take it, then we have to check whether the which one having smaller area if you want to construct a primitive cell. Okay, so yeah, so if you consider unit cell, probably this will work. Okay, but primitive cell, again, you need to yeah, I think this should also work. Okay, yeah. Now hexagonal system, 2D hexagonal lattice you can take. Now there are different ways you can put center atoms here, or so within this hexagon there are actually 6 triangles. Okay, or this is the unit. Now whether you want to put center atom within the triangle, so it depends on you. This is just I'm showing you something, okay. So this for you to work out, okay. So there will be tutorial or homework problem posted, okay, will be posted by this afternoon. You will have, I mean, you play with this, okay, take different type of crystal structures and play what type of things you get. But always keep this in your mind that if you have a new type of structure, so previously as we defined or discussed for graphene, always think about lattice plus basis. That is also one possibility. Okay, so overall the bottom line is, take various examples, do it yourself. Okay, then only you will understand. Okay. Okay. Also, we discussed, I mean, we took some common examples like simple cubic structure. Okay, we figured out coordination number. Okay, the lattice points. Okay, packing fraction, the volume of the cube, and the ratio between the spheres occupied within this cube. Okay, these are the things we looked at. Then we moved on to BCC crystal, body center. So we have one. We also did the same thing for this, and also we extended this for FCC. Okay. And I mentioned that these are very common type of materials. So hexagonal closed plug is another very interesting and important system. I hope at least you understand how things are arranged. Okay, so these are the balls, as you can see, and on top of that you imagine you put another ball. Okay, so in the tutorial problem you will see that if this is A, okay, and if the height is say C, there is a minimum C by A ratio that exists, okay, that you can solve for. And here also you can find packing density and many other things. Okay, another important example was diamond lattice. Okay, because our silicon germanium, these are diamond lattice. Okay, I mentioned that this is like FCC, but as if two FCC lattice are uh, displaced. So one of them is displaced by 1/4, 1/4, 1/4. Okay, this blue lattice are like one of the FCC. You can see this is this. Okay, and now imagine you have another box, another FCC, but that is displaced by 1/4. So it has gone here, and gone here. Okay. Yeah. So now this is very important. So if you have this type of lattice, then you need to figure out again the packing density, okay, coordination number, lattice point, stuff like that. Okay, these are homework problems. Okay. Okay, so I think that was the discussion in the previous class. Okay, any question? Was there any question? Okay, so now let's just focus one of them. Okay, for example, BCC. So this is a unit cell. I hope you are getting this right. So we have one, and there are different blocks. Is it clear? So how many lattice points do you have in this unit cell? How many? So one already inside, and from the corners you have one. So two. Okay, that means this is not a primitive cell. So primitive cell must have one. So this is how a primitive cell would look like. Okay, so but this is fairly complicated and not easy to understand, right? But primitive cells are quite important. Is this point clear? So here we define unit cell because this is easy to understand and intuitive. Sometimes primitive cell is not that easy to deal with the primitive cells. But primitive cells are important. So will you do some mathematics to find primitive cells, or there are shortcuts? There are shortcuts for electrical engineers. Mathematically, definitely you can define. See, for 2D, if it is square lattice or rectangle, it is still okay. You can still find primitive cells. But for 3D, it is very complicated. So there must be some shortcut, okay, or way out. So that is known as Wigner size cell. Okay, so Wigner has given an algorithm. Okay, let me walk you through this. First thing is that you need to, okay, again for simplicity we consider 2D crystals, right? Because that is easy to visualize, and then we'll extend that idea to 3D. Okay, the idea is, say this is the crystal structure we have, and we need to find the primitive cell. So this is 2D, and you know, I mean, this rhombus will be the unit cell, very easy for you, but for 3D that is not that easy. But what Wigner proposed, okay, fine, you have this crystal structure, then choose a point, lattice point. Okay, so now crystal can have lattice plus basis. When I'm saying lattice plus basis, always think of that graphene. Okay, so you choose the lattice point. That's point number one. So anyway, here we don't have any basis. Okay, so say this is our lattice point. Then you find the surroundings. So we have surroundings, okay, and then you join them, these neighboring points. Fine, very easy. Okay, then you do bisects. Okay, perpendicular bisects here. Simple. And now you are getting this surface, right? 2D surface. Yes, that is Wigner size cell, and this turns out to be primitive cell. It's proof beyond the scope of this class, but this works. Okay, the point is, did you understand it? First take a point, okay, here, then connect, take a point, meaning take a lattice point. Okay, then connect that to adjacent lattice points here and then do perpendicular bisectors. Okay, and then you will get either a surface if it is 2D or you will get volume if it is 3D. Then that will be the Wigner cell size. And now, so if I take this, I mean, Wigner cell, I can repeat it and I can get the same crystal structure. And this is primitive. Okay, so I can reconstruct the entire crystal lattice. Okay, is this clear? Is this algorithm clear? Fine. So for 2D, this is easy, right? That's not that difficult. Okay, by the way, a question. Suppose I give you graphene, examples of graphene. Okay, how will you do this Wigner cell size? Could be given in your homework problem. It will be posted today. First of all, if it is graphene, I hope you remember, then you have lattice plus basis. First, you convert or have the lattice points. That's point number one. And then do this process. Okay? Okay? Yeah, questions?
Sir, in the first step, student consider a Bravis lattice.
Considering that will be, yeah, that means suppose I give you graphene, you remembered, right? That hexagon, that is not a Bravais lattice. You need to convert that Bravais lattice considering the basis. You remember we had that 1D chain, we had 2 points, we grouped them together. That is for 1D, very easy to visualize. Do that for 2D, if required, do it for 3D. Okay? First, yeah.
You directly do that in that graphing structure. Directly can't we apply this?
So yeah, no. The thing is, you need to have Bravais lattice. Because graphene is not a Bravais lattice. First, you need to have the Bravais lattice. I can give you a Bravais lattice. For example, I can give you this FCC or BCC, but sometimes it might not be a Bravais lattice. Okay. Then you have to consider that basis and convert that. You need to group things together so such that it is a Bravais lattice. Okay. Easy for 2D, fine. Okay, now we need to move from 2D to 3D. Okay, so example is here. So, but I can tell you this process will be much easier than this cube, or this is not cube, this is rhombohedral. Okay, yeah, this would be much easier than that. So let's take this BCC. Okay, so note that this is unit cell, not primitive, right? That's why we are trying to do it. We are trying to find the primitive cell. Okay, again, we just do this process and see if you are able to do it, then okay, yeah, so then you understand it well, right? Okay, so first let's take a point here. Okay, what are the neighboring points? I actually should be these blue colors. Do you agree? We have 8 corners. Okay, note that we had defined coordination number. Okay, but here you might need to go beyond that. I'll tell you why in a moment. Okay, so these 8 corners are adjacent. You agree, right? Also take these 4. One top, say plus z, minus z, plus y, minus y, and there will be other 2 sides. Not so easy to show here. Okay, plus x and minus x. Okay. Now what I need to do, imagine lines or planes here because this is 3D. So in case of 2D, we had lines. Okay, and when we join lines, we get surface. But here it will be planes. Okay, you need to imagine a lot because this is crystal structure. You need to visualize. Okay, so it will be something like that. Do you agree? Center to here and goes down here and here. If I bisect, so do you agree here bisection would be on this surface? Do you agree? Because these are equidistant. But here this bisects will be within the unit cell. If you understood up until this, then you are almost done. Okay. So now these are essentially planes. Okay. Now you can imagine. So this is a plane. This is a plane. Okay. And if you construct, it will be like that. So here we have this plane. This plane is giving you this surface, right? So how many of them will we should have 8. One top, one bottom. Okay, so this side, that side, plus x plus x minus x plus y minus y.
So the surfaces are perpendicular to the line joint.
Correct.
Between...
Always perpendicular bisectors. Okay, makes sense? It will be flat surface here, flat surface there. Yeah.
So what is the basis of taking the perpendicular for the bisection in the 3D?
Same, whatever you have done. So we had this center atom, we pick that up first. Then we select the neighboring atoms. So we have, at least you agree that 2 to 4 to 8, right, at the corners. Also, I'm saying that you also consider other ones. Okay, now you will know why. So if I only take these 8 atoms, okay, and if I bisect, you will get these hexagons. But with this hexagon, how many hexagons will you have? So sorry, here you have 6, not 8, okay? Or so 1, 2, 3, 4, yeah, 5, 6. So here you should have 6, okay, not 8. So here how many hexagons will you have? 8, right? Because the hexagons are coming from the corners, and it will be within this unit cell. Why hexagon? You need to visualize, okay? Why this hexagon? This is a plane, okay? Yeah. Okay, so but with these hexagons you cannot have a volume, so you need more points. So these are those extra points or extra lattice, okay, by which you can have this extra surfaces, and then you can have this enclosed volume. I can tell you definitely this is much easier than this. It looks simple, but getting to this primitive cell is quite difficult. But this is straightforward, meaning there are ways, algorithm, you just implement it. No difference. Again, choice of primitive cell is not unique. There's one way to define primitive cells. It can look different. That's the beauty. Okay? See, in the previous case, you said, right, we chose this square and you said rhombus. But anyway, I have to check whether that rhombus is primitive or not, but it seems like primitive. So anyway, it can look completely different.
In this case, both are primitive.
Both are primitive. Yes, this is not round essentially. Kind of. Okay? Yeah, yeah. So if you're not comfortable, then fine, take a football. Okay, so in 2D, you can wrap it with hexagons, right? Honeycomb. You can fill the entire surface. Now, if you want to make a ball, you cannot do it with hexagons only. 2D you can do, but for that, how many pentagons do you need? Any football player here? Is the question clear? You have this football, right? Have you seen it? There are hexagons, right? But there are definitely some, it could be 1, 2. You can think about how many pentagons do you need. It turns out to be that without that you cannot have this. Okay, very similar to this. So you want to have this entire volume. So with this hexagon you cannot have it. You need other surfaces which you get from this, okay, neighboring atoms with this algorithm. Okay. Overall, got the idea? So at least do you understand this? That there will be 6 squares, okay, from this, okay, and 8 diagonal. If you understand that, that's quite a bit. I mean, then, yeah, you need to visualize a little bit for that. Okay, this structure is very important, by the way, for this course that you will see later. That you have to visualize actually. See here, this was easy because I can just draw bisect line. Here what you have, you need to consider a surface. Yes, you need to cut this surface. You will have something, and when you cut it from this side, they will touch somewhere. And from this point, it is not very easy to explain. Okay, you need to visualize it. That's what I mean. Okay, so if you understand till this point that okay, there will be 6 squares and 8 hexagons, that's good, because later on you will find a lot of videos and images online and also in textbooks I also show. Try to understand more, okay? So this is not limited for BCC, do it for FCC. For simple cubic structure, it is very simple. It will be simple cubic. Okay. Okay. Now, if it is, so here there is also another important thing. So here generally we define x, y, and z, right? Axis for 3D. But here, anyway, this names will again get back to this point. So the center, okay, the center of this whatever hyper volume we have is called gamma. Okay, some origin. Okay, well, this is defined by some group theory. Okay, there are important directions that you should understand and appreciate. One of the direction is centered to this face. Okay, I mean orthogonal to this square. Do you agree? That's one of the important ones. So see, this is called x. This is called x point. I just give you a brief hint. So you'll see that later on. There is a direct lattice. I just explain in after a couple of slides, and there will be reciprocal lattice. And when we have reciprocal lattice, we'll have Brillouin and you will have band structure and many things. Yeah, so in that case, you will connect it. That's why this name. So essentially, whatever you have, you will see that, find that these are related to reciprocal lattice space and connected to or related to Brillouin. Okay. Anyway, I will explain it later. That's why these are important. So this is along x direction. This is x point. What is another important direction? This hexagon. Centered to hexagon. So centered to hexagon, this is called L point. You need to understand this because later on you see band structures, you will find this kind of letters. Okay, gamma point. Okay, L point, X point. You need to understand. Okay, is it clear? Here. Yeah. So previously, whatever you had. Okay, now this is a complicated structure. If it is complicated, we need to simplify it. So if you define the same Cartesian coordinate system, it will not be good. For example, I just give you one simple example. If you have a cylinder or sphere, will you use Cartesian coordinate system? You will use spherical, right? Because of your convenience. Coordinate systems are for your convenience, right? So here also we'll define our convenient coordinate system, which are more related to symmetry and fundamental group theories. So one important direction, hope you understand, is from center to this. Center is always important, okay? Center to this square, okay? And another is centered to this hexagon. Okay, now there are different points you can define halfway, okay, here, okay, this is halfway here. Okay, now you can define various other points as shown here, okay? But hope you understand what these letters mean. Is it okay? Okay. So that's all from this primitive cells. Now, which points here? Yes, midpoints. Yes, perpendicular bisects, exactly. This is gamma point. So this is a surface, right? Say this is a surface, this is a gamma point. So this is a perpendicular bisect. So this is what it is. So it is not that. So here to here, this arrow is perpendicular to this plane. So here to here, this L is perpendicular to this plane. Then it makes sense, right? Center to perpendicular. When we define vectors, generally, usually it's perpendicular to the plane. Okay, so you need 2 points. One is this gamma point, center, and another is center of these surfaces. One is we have this rectangle, so yes, and squares essentially. Another one is hexagons, and there are also other points defined to capture all other informations. Okay, for example, center, I mean midpoint here, okay, join here and there, but these are 2 important ones. Okay, yeah. So physical significance of this, manifold. First thing is that you need to have primitive cell. Okay, so what I try to tell that in 3D, finding primitive cell is very difficult. You need to be a very good mathematician. So Wigner size, provided the algorithm. Okay, if you follow it, you can get a cell. It might look complicated, but definitely you will get a primitive cell. This is what it is. Okay, point number one. So point number two, later on you will see that direct or crystal space and reciprocal space. Okay, so yeah, I mean this edge, whatever we have, okay, the boundaries, these are related to Brillouin zone boundaries. Okay, and many important things, electronic transport, band structures are related to that. We will get into that soon. Okay. Any other questions?
Sir, I did not understand why they are taking the atoms outside of this.
Yes, don't take it. If you don't take, that's a very good point actually, because it confused me. So initially I saw that lattice, what is the coordination number, each, right? Why not only here? Why to go beyond that? Okay, the reason is if I take only these points, we have these hexagons. Now imagine you have those hexagons at the corners, but those hexagons cannot make a volume. That's the thing. No, it is not that you are taking. It is what is happening. You are not taking anything. You have this crystal structure and you consider planes. You take infinite plane. It's not an issue. You take planes here. But whatever planes you have, if you don't consider these, so this corner, so after doing this perpendicular bisector, okay, these planes cannot produce a volume. If it cannot produce a volume, you won't have Wigner cell size. To have, one second, to have that volume, you need these extra points. Then only you have. Then what you have these planes, and when you combine all the planes, essentially you get hexagon here and square here. Now you need to visualize more why hexagon, why this. Okay, that's not that easy to explain. Yes.
Sir, let's say if we leave out the atoms from the outside world,
Right.
and when we got two hexagons and two hexagons, like four hexagons,
Then actually you don't know what is happening. So you have the planes. You extend it and see how it goes. So whatever you will have, there are two possibilities. One is that either it will not form a volume, or if it forms a volume, it will be bigger without these points.
we don't have an access point.
Exactly. So you will not have a volume. Okay, that's why this is important. So that's why this is very crucial point, that this could be different from the coordination number. You need to consider, that's why I said neighboring. Neighboring meaning, okay, it has a different meaning, different places. So you need to consider neighboring points such that you get enclosed surface for 2D or enclosed volume for 3D. This is very important. Okay, so now this was for BCC, you need to do for FCC. Simple cubic structure is very simple. Okay, those will be your homework problem. Sometimes if it is not given in homework problem, whatever I'm saying, remember, write it down and do it. Because most of the time it happens that whatever I'm leaving as homework problem, those actually appear in exams. Okay, yeah. I mean, you can ask your seniors. Yeah, it's pretty much consistent. Okay, so now you guys know how to find primitive cells. We are all good. Now important thing, planes. So we have crystals, we have vectors. So define different planes we have, right? Now we need to, have some reference for that. We have to name them. Okay, given by the Miller indices. Okay, again there are processes, very simple process. For example, let's take this simple cubic structure or simple cubic lattice. Okay, for example, how to define this plane or how to name this plane. Okay, first point is that, okay, you need to find origin. Okay, let's consider this origin is here. Just don't put the origin on that plane. Okay, just put it somewhere, anywhere in the lattice. Is it okay if I put it here? That's point number one. Then you find whatever plane you have, you try to find what is the intersection length. If this is A, atomic spacing. If this is A, what is the intersection? Here, along X, no intersection, infinity. along y, a, and then along z, infinity, right? Then invert them. What do you get? 0, 1 by a0. Is it okay? Then multiply with suitable number such that you get integer. So here if I multiply with a, I get 0, 1, 0. Yes, so this plane is defined 0, 1, 0 planes. 0, 1, 0 plane. Can it be 0, 2, 2, 0? I can multiply with 2a. It can be, because we don't have just a single plane. There are parallel planes. All are there. Instead of saying 0, 1, 0, 0, 2, 0, all belong to a set of planes. Okay. So what about this plane? Can you find Miller indices for this plane? Very good. Like this? Okay. So these are called equivalent planes, generally defined with this curved bracket. So for cube, simple cube, so this plane and anyway, there are parallel planes here. For example, 0, 1, 0, 0, 2, 0, they are exactly same. But here, these two planes are also identical. Because whatever lattice environment you have for this plane, you have the same environment here. So this is also an equivalent plane. So how many equivalent planes do you have? 6. Do you understand that these planes are same and identical? Okay, so these are defined with these vectors. Okay. Now let me give you another plane so that you find a different type of plane. Okay? Then you will understand what is the difference between equivalent plane and inequivalent plane. What about this plane? This plane is different, right? Certainly different from these two. Find a Miller indices for this. Okay, again you okay. So why is it intersecting x axis? Infinite. Y, z, then like that. Okay. So how many equivalent planes do you have for this case? Okay. Okay.
Sir,
Yeah.
sir, how we decide suitable number?
Any. You multiply one a, generally multiples of a to a. But if you say 0, 2, 2, it is same as 0, 1, 1. If you say 0, 3, 3, same as 0, 1, 1. Better to say 0, 1, 1. Okay. Okay. Now we have crystal planes. So whenever you have crystal plane, you can define crystal direction. Very easy, perpendicular to the plane. That's crystal direction. So here, so whatever we have, we are referring y. How do you define it in this with this language? So 0, 0, 1, 0, 0, 1 direction. So 0, 0, 1 plane is this one. Sorry, 0, 0, 1 plane is this one, right? And perpendicular to the this plane, which is z, that is called 0, 0, 1 direction. Okay, I think yeah. So this is 0, 0, 1 plane shown with the curl bracket, and here with this straight bracket. These are just definition. This is how it is defined. Is it clear? You know, right? That perpendicular, the direction of plane is perpendicular to it. As simple as that. Okay. So now if we have different equivalent planes, we'll have different equivalent directions. So here this is defined with this this arrow. This is a definition. If it is plane, it is shown with this curl bracket. If it is this, is just definition. If it is direction, it is defined with this. Okay. So now, so we can have plus and minus with reference to your origin. Okay. So if it is say minus y direction, instead of saying 0 minus 1 0, it is here shown 1 bar. In detail you have seen, right? Minus something like 1 bar. Yeah, it is just bar. It is the definition. Okay. So now if we have planes, that means when I'm saying planes, definitely I mean we have the crystal directions as well. Okay. So if I give you two planes, two different planes, you can have angles between them. Right? This is very simple. Okay, just like a vector, if I have vector A and vector B, how do you find angle between them? Right? A dot B, same thing here. So this is our definition here. Okay, this is like a vector only. With the, I mean, as defined by Miller. Okay, you can do the same. So just check if I take these two crystals, I mean these two planes, say 100 and 001. What would be the angle between them using this formula? Are you getting 90 degree with this? Making sense, right? What about this if I take this plane 110 or whatever 001, okay, and 100, what will be the angle? 45? Are you sure this will be 45? Okay, yeah, so this is very simple, but we have many other variants, right? We have BCC, we have FCC, we have HCP. So then your job will be to do this for other planes as well. All planes. Don't leave anything, because always remember whatever you leave, that will come in exam. Okay. Some of these questions will be there as homework problem, but we may not include everything, right? Yeah. So you can calculate. I'm not saying yes or no. This is a question. You can very easily calculate. Yeah, index by index. Tell me what do you get? I didn't say it will be 45. I just said okay. Because I know you can do it. And this is not the only example, right? There are many. We can have BCC. Tell me what are you getting? Tell me. Multiply these two guys. What are you getting? What are you getting? 0, 90. Okay, let me see. What do we have here? We have 100. 100 is this plane. Acha. I should have given some other plane. Very good point. What is the angle? 90 degree, right? The reason is, so one plane is going like that. Okay, I think you guys got confused with this. Okay, if the other plane is like this, if this plane is that, then you have angle. But right now, what is given here? So these are perpendicular. Okay, that's why you are getting 90. Is it okay? There are different variations in questions, right? You can, I'm sure you can do it. Okay, there are different, okay, fine, conceptually, okay, a very good point. Okay, let me see. So, yeah, also, I mean, we have BCC, FCC, many other options, I mean, many other variants. So we can make it slightly complicated. We can go to this hexagonal closed-pack system. Again, we can define two axes, but it is better to define three because of this structure. Again, I'm repeating, we have coordinate systems for our convenience. Okay, if we have this type of structure, then it is convenient. Okay, here again, same story. For example, here again you need to find that intersection, and you need to figure out the planes. Okay, this will be 0001 because this plane is not intersecting any of these A1, A2, A3 directions, correct? It is only intersecting the C axis. But if I take this one, then it is intersecting here. Okay, I think in 1 minute or 2 minutes you will not learn it. Solve it. Okay, you have enough time. Is it okay? The point is whether you understand Miller indices or not, whether you get how to this algorithm, then you need to implement it. Okay, take various examples, as many as you can, solve it. Okay, there will be questions based on that. Yes.
Sir, how do we go about finding about XCC and BCC? How do we approach it? Which place are you considering? The primitive cell one?
No, no. Here, okay. So the thing is that uh, some plane will be given. Suppose I give you a crystal structure. A plane is given. Your point is you need to find uh, a coordinate system. Okay, you need to find 0001 on the lattice point. Okay, you define your coordinate system. You have the origin. You have x, y, and z. That's why this unit lattice are important. Okay, that's why we have for a simple cubic is a simple. If it is FCC or BCC, take the like XYZ coordinates, which are 90°. Okay, now it doesn't matter where you are defining, whether from the center atom, which atom. Just define it at your convenience. That's all. But what I'm saying here, if it is hexagonal closed pack, okay, it is advisable if you have 3 in-plane vectors for defining them because of this 6-fold rotational symmetry. This is how it is done usually. Again, you need to see like the intersection. For example, you can just consider this one. This is simple. So this plane, it's intersecting this guy, right? Say A1. So this is parallel to this plane. Say this is A2. Okay, that's why it is not there. Okay. And it will not intersect Z. Okay. And eventually for this A2 direction, it is going in the other side. Are you getting? So this is A1 from center to outward, A2 and A3. Sorry, this is A3. Okay, for A3, that's why we are having 1 bar. Just follow this. Just try to find the intersection. So do you agree that along A1, it is intersecting at this point A? Agreed or not? So along B, is it intersecting anywhere? Infinity, right? It is not intersecting. Along C meaning, I mean, sorry, X, Y, okay, it's A1, A2, so A3? No, so this is this direction, right? If I take it here, then it is intersecting here, right? Minus A and along C, yeah. And along C, you please go, yeah. And along C, Z-axis, no intersection, right? Okay, so you can do the same. This is not the only plane you have. Take different cases. Okay, fine. Okay, yeah. So this is how we define planes, crystal planes. Okay, now the question is experimentally, is there any way to probe this information? The answer is yes. Acha, before that, okay, so yeah, before that there is another thing. Okay, so in the real space or crystals, we have seen this periodic arrangement of atoms or lattice, right? So when we have this periodicity, we can definitely do Fourier transform. Okay, so now, so this is sine wave. I think electrical engineers are more familiar to time ft versus t. Here we are doing fx versus x. If it is 1D, xy versus x and y, right? If it is 2D, okay. So now if you take this sinusoidal, okay, if you take Fourier transform, what do you get? Sorry? Impulse. 1 or 2? How do you visualize that or intuitively understand why 2? Omega 1 and minus omega 1, right? Sorry, omega and minus omega. Are you saying this y plus and y minus? How do you intuitively understand? Sorry? Then? Yes, e raised to I omega t plus e raised, sorry, minus e raised to minus I omega. So plus I omega t, that omega comes here minus, and see in between we have a minus sign. If I don't take modulus, it is changed, right? If it were cos, it would have been same sign. That means continuous signal in time domain get questions essentially. Continuous signals periodic in time domain or position domain will give you discrete in reciprocal. So if it is time domain, we call it, I mean, after Fourier transform, we call it frequency, right? But if you want to make it general, we call it reciprocal space because it is not about time. I can do the same with x position, space. Better to say reciprocal. Okay. So for you, again, get question, if I have series of impulse functions. So this is periodic, discrete. There are four variants essentially. If it is periodic, generally also in interviews, this kind of questions are asked. If it is periodic and discrete in time or space domain, what do you get? Sorry? Anyway, you can do it, okay? Standard problems. In signal system, in the first chapter, you will see. Okay, it will be discrete and periodic. Other variants anyway, you can look it up. Okay, so essentially what I try to mean, so this is time domain to frequency domain, and if we are here we are working on position. So position will go to k wave vector that is related to momentum. I'll connect maybe in today's or maybe in the next class. Oh, okay. So yeah, this time to frequency, and you will see that frequency is nothing but energy, and position to k wave vector or momentum. Okay. So this is the direct space and this is the reciprocal. Okay. These are the things. So now you know if it is discrete and periodic, we get discrete and periodic. So this is our typical simple, square, 2D square. So it will be like that. Okay. But things can be complicated, right? Later on. Okay. So for that, you need to do the Fourier transform. So in textbooks, you will find equations. So here, I'll not go into that. Okay. So rather, I just give you straightforward expressions. Derivations are there. I just show you after class from where you will get it. So now, if you know real space primitive vectors, say A1, A2, A3, let it this be in 3D, then you can find the reciprocal space primitive vectors. Okay, and this is how you can get. I'm not deriving it, I'm just giving you straightforward. And whatever expressions you had for the time domain, same thing also applies here. Okay, just the discussion is slightly different, which you'll find in textbooks. Okay, so if I give you 2D, then what you can do, P3 you can consider Z. Okay, then you can find it. So in tutorial problems, you will see that for 2D, we'll give you hexagonal closed back systems, hexagonal systems or graphene. Okay, you can do the Fourier transform, see how to get. These are standard things you will find readily. Answers will be available online. You can also do it. Okay, yourself. Okay, but some 3D things you need to derive, which we are not deriving here in class because there is no point. So those are homework problems. Again, I'm repeating, this can be given in the homework problems. If not given, if I'm saying, you should do it. For example, if you have simple cubic structure, use this and see what you get in the reciprocal space. So here you have seen that this kind of discrete becomes discrete, right? There is no change. So you will see that the simple cubic will be simple cubic. Okay, that you will see. I'll just show you in Kitter's book, these are derived. Now BCC. If you do BCC, you will find that BCC in real space becomes FCC in reciprocal space. That is very interesting. That means when you have BCC lattice, you need to find primitive vectors. So, and you put these vectors here and see what you get. So you will get some vectors, and eventually those vectors are primitive vectors for FCC, and vice versa. You have seen the Fourier, this essentially common in Fourier. If small ft becomes caps of ft, caps of f omega, then if you do caps of cap f t, it will be small f omega, right, with some constants. So if BCC becomes FCC in reciprocal space, FCC will become BCC in reciprocal space. HCP you should do. Okay. Is it clear? So are you getting the reciprocal space? Yeah. Let me give you a hint that in time domain, okay, our reciprocal space is frequency. You can relate. Frequency of train, this and that, okay? So here in position, the reciprocal space is wave vector. And that wave vector is connected to momentum. I'll explain it, okay? That means if you have the crystal structure and if you do this F50 Fourier transform, or if you know the reciprocal space, essentially you get the wave vector profile and you know momentum space. Okay, you get the momentum space. And when you have carriers in crystals, instead of saying carrier moving, you can actually track its momentum. Both are same, just two sides of same coin, will give you same story, unlike our news channels. Okay, so instead of, so you want to find current, right? You want to track electrons in lattice, rather track their momentum in momentum space. That should give you same result. That's why it's important. Anyway, I have not mentioned which materials have which crystal structure. You will find sodium chloride, you can take copper, you can take iron. You should just skim, okay, just fine. But importantly, silicon, germanium, these are diamond lattice. Diamond lattice are nothing but FCC lattice with basis, right? I mentioned two FCC lattice, one of them shifted 1/4, 1/4, 1/4. That means, okay, so diamond lattice is nothing but FCC with basis, just the way you had graphene, right? You had graphene with the basis, right? Similarly, diamond lattice is FCC. And that is of our interest because silicon, germanium, this semiconductor, gallium arsenide, majority of them are diamond or zinc blend. Okay. So we are interested in FCC here for this course, FCC in real space. FCC of real space becomes BCC in momentum space. And remember, we already discussed what primitive cell looks like for BCC, right? That type of ball. That means for diamond, we have, silicon, it is diamond or FCC lattice in real space, and its reciprocal space will be like that as we discussed. Okay, that's why these are important, and that is nothing but the momentum space, whatever we discuss. So the momentum space along different directions. Okay, so that means along different directions, crystal behavior will be different because of single crystal. Okay, these are the things we will continue. Okay, one last point. Now we need to find anyway, we don't have much time. I thought we would start quantum mechanics, but anyway, we cannot. But here,
Position and momentum space was
so
from the BCC or FCC.
that you have to calculate. The question is like, if I give you if I ask you to do Fourier transform of one signal ft, f1t, if I give you another signal f2t, for that you need to calculate, right? These are the things you have calculated, right? You have different signals. You know how to calculate them. Same here.
Derivation domain.
I need to pause this video, otherwise I cannot go. So in the previous slide, I have given you this equation, right? If you know the real space primitive vectors a1, a2, a3, you can find primitive vectors for reciprocal lattice. The formula was given. You can use that formula to finding it out. Now, if you ask me how to derive that formula, that's a long derivation. That we are not doing. I'll show you in a moment where to find it. So that B1 was A1. Okay, that formula. Unfortunately, I cannot go back here. Okay. Okay, now very quickly. Anyway, XRD is a big topic. XRD is something, a technique by which actually you can probe planes. Okay, X-ray. So these are single crystal materials. So we shine it with X-ray, and something is, yeah. So it penetrates, diffracts, and we have interference. Okay, and this interference pattern is recorded. So to have the constructive interference, just the way you had that for double slit, Young's double slit experiment, this is how it goes, given by Bragg's. Okay, so this is the path difference. Interference is essentially the path difference. If it is proportional to lambda or equals to n lambda, you get interference patterns. Okay, and from that you can actually know what are the planes, what plane you are probing. The reason is, if you have a different plane, this path changes. When the path changes, the interference intensity will take place at different position. And if you do for all the planes, then you know for which plane where it appears. There is a chart. Right now you don't need to do anything. It is there already in a library. People have studied everything. So what people do, suppose you are growing a film or material. Okay, then there is a system, you do this XRD measurement. Okay, and you analyze this kind of peaks, where peaks are arising. It just might happen that they will not arise. You didn't grow a single crystal in that time. Okay, so if peaks are arising, then you compare where. So if I have peaks here, what does it correspond to? Okay, and from that you will know different planes. Okay, so now if you know different planes, that essentially tells you have single crystal material. Those things are ordered, but you are not capturing all the points, right? It is the other way around. You know the planes exist, and from that our takeaway point is that yes, the material is single crystal, but we can have other way around. So I have shown this kind of image. These are called TEM image. Okay, transmission electron microscopy. So idea is very simple. You have very thin film. Okay, I mean, say this width is 10 nanometer. You can thin it down. There are techniques. Okay, you cut, slice, and you can really make it 10 nanometer. So this height can be anything. Then what you do, you shine it with electron beams. So it is highly accelerated. And by the way, before that, for this diffraction, why X-ray? Why not photon? I mean, our UV light or photon, or our UV light or something else. Why X-ray? Huh? No. So here, the thing, if it is light, you know, right? So you have a mirror, you shine light. What do you have? It reflects. It has atoms, but what happens? The wavelength of light. Sorry, it is getting a bit longer. Wavelength of light is much bigger than the atom size. So they cannot. See that discreteness, because it is much bigger than that. So, there is something called grating effect to get diffraction. That will only happen if the wavelength is comparable to this lattice dimension. X-ray satisfies this. That's why X-ray. And that's why the reason X-ray can penetrate quite a bit. Suppose you have a thick sample, it can penetrate quite a bit and you can still get the signal. Okay? That's why X-ray. But when you want to image it, it's a different thing. You make it very thin. You make it thin. Okay, say this is like a 10 nanometer, 10, 20, not more than that. Then you shine it, or you illuminate this surface with electron beam. Okay, so later on you see the electron as a wave particle duality. Electrons are particle, but it also has a wave nature. You can associate some, we'll see that in next class, that lambda wavelength is there, and that is, you can tune that with the energy to the electron, and this can be much smaller than the atomic dimension. Then what happens, wherever you don't have atoms, it just passes, And whenever you have atoms, around that point, you have the diffraction in electrons, and you get the diffracted pattern. And from that diffracted pattern, you can get this kind of nice images. So this image, from this image, you exactly don't know what is this plane unless you are very expert. But this is like the way we take our photo. But this is done using electrons. This is not, there's a difference. That's not surface. This is a cross section, side views. This is not for X-ray, that is from the surface. Okay? This is a cross section. Everything mostly passes, all electrons. Because electrons wave length is much smaller than this atomic spacing. But wherever it is close to that atoms, you will have diffraction and you get the pattern. And by by analyzing that, you can have this kind of image. That means if it is thick, the problem is that, I mean, so this electron, I mean, this entire thing will be blurry. This is cross section. This is a cross section. Not, say, there are two things. One is that you are growing samples like this. So you can view from the top, you can view from the side. So it is view from the side so that you can see different layers, how layers are actually oriented. You can see from the side. Okay, so from here you get direct image, and analyzing this you will know crystal structure, planes, everything. XRD is other way around. You know crystal structure, plane. So this directly tells you we have single crystal material. That means we have this plane, that plane. And when you do XRD, you get the planes, get the information of planes. That means indirectly or directly, it infers that you have single crystal material. Anyway, XRD is a vast topic. There can be several lectures on that. Yeah, theta to theta things. Anyway, I don't have time. Maybe I can explain it later. So there are some YouTube videos. So I just given this link. You can open and see how actually XRD is performed. Okay. Anyway, okay. So that's all. So before you leave, I just want to very quick